Bismillahir Rahmanir Rahim. So we are back with our part 2 of our previous lecture, that was crystal field splitting in the octahedral metal complexes. Metal complexes which have 6 ligands. So they have the octahedral geometry designated by denoted by OH. तो इसमें पार्ट ए में हमने कुछ पोर्शन डिस्कस किया था, बाय सम रीजन हम उसको कंप्लीट नहीं कर पाए थे. Now in the part second we'll try to finalize this, complete this crystal field splitting in the octahedral complexes. तो going back, हमने कहा था octahedral complexes में when the ligands approach 6 ligands, they approach the metal ion from the 6 sides of the octahedron. So there's a repulsion occurs between the lone pair of electrons on the metal and the electrons on the d orbitals of the ligands. That repulsion results in the this type of situation, 3, 4, and 5. Then we have the two orbitals, they split into T2G set and EG set. So these are the two orbitals, is designated as T2G set, and this is called as the EG set. ठीक. So these orbitals where ये जो जिनकी एनर्जी कम हो जाती है, ये जो अपना सेंटर ऑफ ग्रेविटी है जिसकी एनर्जी 0, we're considering it 0. So this is your this is your T2G and EG set. So this is third. So dxy, dyz, dzx. तो ये वो ऑर्बिटल्स है जिनकी इलेक्ट्रॉन डेंसिटी इन बिटवीन द एक्सिस है, जिनके लोब्स इन बिटवीन द एक्सिस लाई हो जाते हैं. एंड दीज टू ऑर्बिटल्स dx square minus y square, this is dz square. So इनकी इलेक्ट्रॉन डेंसिटी is lying along the axis. So that's where they are experiencing more repulsion. तो ये हमने पिछले क्लास में डिस्कस किया था. So this splitting, मैंने कहा था, of the d orbitals, we can see that the d orbitals now in a metal complex, where we have complex formation, the degeneracy of these d orbitals is lost. So these are 5 d orbitals on the metal ion. So these are d orbitals. So this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So their degeneracy is lost. Earlier their energy was same when they were present in the metal ion, which was free, but in the complex formation now, so they got split into the two sets. So we said that this energy difference between the two states is called as a crystal field splitting energy. This. So this difference between the two is called as a crystal field splitting energy. Crystal field. So this is called as a crystal field splitting energy. The difference between the energy of the two states. Crystal field splitting energy or crystal field stabilization energy. Stabilization energy. It's called CFSE. You get अपना crystal field stabilization energy. Now it's an octahedral complex. It is designated by delta O. O stands for octahedral. तो मैंने कहा था, let's just make it. So ये जो orbitals है, these two orbitals, dx square minus y square, they are splitted. They got elevated, they got raised in the energy because of strong repulsion. So this is basically, this gap is 0.6 delta 0. ठीक, that is your 3 by 5. That is your 3 by 5. That's 0.6. So these three orbitals, they are lowered by energy. Their energies, the net result is that in the complex formation that they got lowered in the energy, and this value is equivalent to, it's 0.4 for each. So that is equivalent to 2 by 5. Tick. So this was the crystal field splitting in the octahedral complexes. Fine. Now, अब ये जो extent है, extent of this splitting, एक जो major factor इस extent of splitting के लिए है, that is one of the main factors for this splitting, that is the nature of the ligands. So we'll write here by saying that one of the major factors. So one of the major factors for this crystal field splitting in octahedral complexes, it is that it depends on the nature of ligand. Nature of ligand in the complex. एक metal complex में ligand कौन सा है? Means, let us understand this. We'll take two examples. We have a complex of iron, hexacyanide, 3 minus. This is one complex. And one more complex, it is Fe. Same complex, fluoride, 4 negative. Now in both the cases, हमारा metal line is same. Number of ligands is 6. They are octahedral complexes. But in this case, now this, we say that in this case, the pairing takes place, pairing of electrons. In the pairing of electrons, को मैं ज़्यादा discuss अभी नहीं करूँगा. So in this case, क्योंकि this ligand is considered to be a powerful ligand, strong field ligand, it generates a strong field, and because of that repulsion, the electrons get paired up in the 3 orbitals, 3d orbitals. जब paired हो गए 3d में, so इसकी hybridization बन जाती है d2sp3. This is your 3d. This is not 4d. This is 4s. And these 3 orbitals are 4p. So since inner d orbitals are involved in the bonding, so it's called inner orbital complex. Inner orbital complex. क्योंकि इलेक्ट्रॉन्स की पेयरिंग हो गई, नाउ इसकी जो नंबर ऑफ अनपेयर्ड इलेक्ट्रॉन्स है बहुत कम हो जाते हैं. आई विल नॉट गो इनटू डिटेल्स हियर. सो इट बिकम्स अ लो स्पिन कॉम्प्लेक्स. Low spin complex. I will probably take one class for this in the next, where we'll explain how at least this and this, this is forming the low spin complex. So this whole is because of this ligand. It's considered to be a strong field ligand. But in this case, same is the case. In this case, no pairing of electrons takes place. No pairing. क्योंकि इसका फील्ड जो फ्लोराइड का जनरेट्स अ वीक फील्ड, उससे जितना स्ट्रांग नहीं होता है, which is not enough to make the electrons to pair up in the d orbitals. So no pairing of electrons in the 3d orbitals. इसका मतलब है they are no more available to make the bonds. So the hybridization is sp3 d2. So this d2 is the 2 d orbitals are involved in the bonding. They are basically the 4 d orbitals. So in this case we have, this is 4s, this is 4p, so this is 4d. Actually 4d is the outer orbital, it's called outer orbital complex. So this type of complex, it's called as a outer orbital complex. Now in this case, since pairing is not taking place, that means we have more number of unpaired electrons in the d orbital, so it becomes a high spin complex. So the weak ligand, they are giving a high spin complex. So this is the basics that, so why it takes place, because अगर gap ज़्यादा बन जाती है ना, if you have a stronger ligand, that will cause the greater repulsion, that will cause greater splitting, field splitting. अब अगर electrons आपको add करनी होंगी, you will add first from here 1 1 1, और अब now क्योंकि gap बहुत ज़्यादा है, you cannot make the electrons to put here ताकि आपको it looks like pairing. You know, electrons will not remain as the unpaired, so they will better, क्योंकि difficult है फिर यहाँ से electron यहाँ add करना. क्या मतलब? Let us say example. Let me rub this. Usually, for like, let us say we have a D5 system. An example, just making an example here. Let us take an example that we have a D5 system or a D6 system. For example, so D5 system में अगर हमें electrons को fill करना हो, example ले रहा हूँ. So we'll make it like this. 3, 4 and 5. So we'll first put one electron here, then here, then here. Okay, 3. A usual trend is that we should first fill the one in each orbital, because so as to have the maximum multiplicity. Honda's rule of maximum multiplicity. लेकिन if this gap, अगर ये gap, splitting gap बहुत ज़्यादा हो, it is very difficult to place the electrons here. So they will not follow this path, rather they will follow this path. That you will fill these two. The result is that you have no electron here. No electron here. That means now we have only one unpaired electron. अगर ये gap बहुत कम होगी, you can fill the electrons here. So you have 5 unpaired electrons in that case. 5 unpaired. In this case, it is 1 unpaired. So it depends on. So same as the case here, I told the pairing of electrons when we have Cn, because it creates larger splitting. So in nutshell, so this crystal field of splitting, it depends on the nature of the ligand. So based upon कि किस type का ligand है and what is the effect of it is splitting. So a series has been made, an arrangement has been made of various ligands in increasing order of their crystal field of splitting. So we'll arrange the ligands in the increasing order of their crystal field of splitting. Iodide ligand, bromide ligand, S2 negative ligand. We can take chloride. कुछ मेन जो ज़्यादा यूज हो जाते हैं कॉम्प्लेक्सेस में, फ्लोराइड. सो ये हैलाइड का सीरीज. सो इट इज आयोडाइड, दिस इज फ्लोराइड. So fluoride is a better ligand than iodide. Then hydroxide. Then we have your oxide. Then we have your water. Then ammonia. Then we'll move to this side. So just moving from here. I will start from here. So your ethylene diamine, NO2 negative, Cn negative, and CO negative, CO, carbon. So we can just show it here. So this is the order, increasing order of the power of ligands, the strength of ligands as far as their crystal field splitting is concerned. Means अगर हम यहाँ से आगे चले increasing order में, तो जो ligands यहाँ पे है top पे, they have a stronger crystal field. They will create the splitting the two orbitals more in the octahedral complex. So these ligands are on the higher side. So they're called as strong field ligands. So they're called as strong field ligands. They're called strong field ligands. And those ligands which are on this side, they're called as a weak field ligands. Weak field ligands. So जब ये weak field ligands है, that means their complexes will be low, their complex will be high spin complexes. While as ये जो complexes बनाएंगे, they will be, क्योंकि they will cause the pairing of electrons, so they will be low spin complexes. Low spin complexes. And this series, this arrangement of various ligands in increasing order of their crystal field strength, this is called as a spectrochemical series. So this is your spectrochemical series. Spectrochemical series. Now this spectrochemical series also is an interesting topic to discuss. Why any ligand we have, those ligands here. Why water is here, its OH negative is here, it looks like charged, why it is here, should be here. ये एक important topic in the future we'll put it, but looking at the level here, so this is the basics what we need at the moment. So this is the basic concepts of the crystal. These are the basic concepts of crystal field splitting in the octahedral complexes. अब इसमें और एक example है, जो iron की example और मैंने दिखा था iron cyanide complex and iodine fluoride complex. Inshallah, in the next class we'll take a brief. We'll in the detail we'll try to explain that how high spin complex is formed with sp3 2 hybridization in case of fluoride complex and D2sp3 in case of cyanide complex. So that inshallah we'll do the part number 3 tomorrow. So till then I believe this is enough. So this is all about the crystal field splitting in the octahedral complex. That was the part number 2.